Welcome, welcome everyone to this live stream here, FPGA Verilog goodness of our video core with even a RISC-V, Pico RISCV. It's just repositioning some stuff. So if you have not seen the previous video, this is already the fifth or sixth, seventh installment here of this sort. And previously, if you're interested in these details, maybe want to watch this previous videos where we did all the unboxing and initial enablement and all this fun stuff, and learned a lot with Verilog. And we've done here this video core, meaning some VGA-like video signal in either shades of gray or color, and in the meantime even the more complex, because from one character in memory, one 8-bit like an H, and so on with color attribute, multiple pixel generating there on the fly. Surprisingly more difficult than I expected. Learned a lot at this initial stuff there, and again previous videos. So previously we had this running freestanding without any CPU integration, but of course we also tested the Pico RISCV open source implementation, and of course we want to drive this from software, and I finally got this to work a little bit. And again, each of those steps was more difficult than I thought, mostly actually because you always think trivially, I just connect this bus or something, and then it just doesn't work by itself so easily. For example, just bring this stuff here a little bit. For example, you would think, yeah, just some bus, let's just connect this. But basically, especially if you're getting used to it, the problem is that the registers and wires, or especially wires here for connections, they can have only one driver. So if we go to the icebreaker here, so previously here was some memory mapped or IO mem. So this is basically here what was already existing in the Pico RISCV icebreaker example, and I thought, yeah, I just connect somehow to this IO memory bus. It has here write and read data, the address, which bytes of the 32 bits, so this 8 octets, this 8 bytes, which of those are written for unlined access or 8 and 16-bit writes and reads, or actually this is for writes, and so for only writing partial data, and whether this IO mem is valid. So for example, if you write in your program, you have some pointer of some sort, let's say this is the whole system memory, and you index something like 64K or 640K or whatever equals something like 1, 2, 3, 4, whatever. This would generate, as per the previous videos where we looked into MIPS and RISC-V instructions and architecture, this would be a store, or x86 also, so some in x86 move to this pointer, and this of course generates the signal on the address line. So basically this address line of the CPU would then hold this address, and so this valid means that whether this IO memory is valid. So it could also be the SRAM internally. So this means this address here, I think everything over 1 megabyte or something of that sort. Depending, of course, this is open source, you can change this. Anyway, so this bit, so if you don't have here any other specifications, this means here 4 bits from 0 to 3. If you don't have here anything, then in Verilog by default this is just 1 bit. So this is a wire for connection, and this is a buffered register. This is ready signal. So how this works is the Pico RISCV, also if you were wondering how this looks, so this is Pico RV32 Verilog. So this is a Verilog of a real CPU. This fun stuff, maybe we take a closer look another day. So when this, so for each clock it generates whether this IO mem is valid, and the address here obviously, and I thought I just connect this. I added this here to the VGA core. This is our code here. And this is already the 5th iteration. Of course, the previous 4 attempts didn't work. This is already the working version. But initially I thought I just connect everything here to IOMEM, and then of course I got some Verilog warnings and errors. For example, that this ready, this ready and so on has already a driver. So for example, to a wire you can only have one driver. Turns out this IOMEM was exclusively used for this GPIO, for the blinking LEDs here. You see here always positive edge on clock. Here this IOMEM. This is how the system IO memory bus works on this Pico SoC. This is basically the address decoding. You see here if not reset negative, like inverted, then GPIO initialized to 0. Otherwise, if not in reset negative, then assign here IOMEM ready, like we are not starting with not ready. And then if this is decoding for us, like IOMEM address this bits, here this high bits 3, then this is GPIO read write to this LEDs here. They are of blinking lights fame. And so as you see, we cannot just add our code there. First of all, our code is in another module. And second of all, we cannot have 2 drivers. So if we would write to the same wires and address buffers there, Verilog would warn anyway. Welcome everyone, by the way. So the way I solved this is, they had already code here in this Pico SoC. Where would that be? Like for the simple UART. So they have here a simple UART. So basically I usually look for other examples, and what is already, why is this not, maybe this is in Pico SoC. Let me just quickly open here. So maybe it's in this file. Yeah. So in the other Pico SoC module, the way this works is this icebreaker module is reusing here this Pico SoC module and just extending it a little bit in good old-fashioned modular design. And as we can see here, for the simple UART and other devices, so we have in Flash and SPI Flash, here SPI MEM and simple UART. And I was looking into this, okay, so how this works here to connect something to this Pico SoC RISC-V system bus is to have here to generate a dedicated select wire signal. And as you can see here, they use MEM valid. I just need to check, just not the most convenient. Yeah, probably showing the right thing. If memory is valid and the address is this address, this is the SPI memory IO, or here in terms here other addresses for the simple UART divide and data register. They have here dedicated select specifically for the divisor and the data register here. So of course we cannot just copy this because we have more than like 2. So basically they have here a dedicated address line, a select line for just these 2 registers. Of course for our VGA core we have way more than 2 registers, so we cannot just copy it like this. But and then also you see here the data, the decoding. They have here if IOMEM valid and IOMEM ready and SPI MEM ready and RAM ready and SPI MEM IO select and so on, then assign this MEM ready here, for example, or read data. So MEM assign MEM read data. If this works, if MEM valid, IOMEM valid, then IOMEM R data. Otherwise, so this is IOMEM read data. Otherwise, a huge statement. You see, this is totally C-like. Otherwise, if SPI MEM ready, then SPI MEM read data, and so on. So given the structure, it looks a little bit unreadable, more unreadable than it is. Given the structure, I replicated this here for our icebreaker video module that is running here right now. And so I have done this here similar. So we generate here a wire VGI MEM select, and I basically say, okay, for our video core we have 32-bit 32-bit address space anyway, which we mostly don't use because we have a super tiny FPGA. So let's just, for the video core, just use the whole upper half of the address space here with the 31st bit set from the IO-mem address. So if basically if our RISC-V core generates the IO-mem valid signal and the address is the highest bit set, so everything over 80 million or something hex, or 8000 and for more zeros hex, then this belongs to our, we basically take all this IO, like half of the whatever excessive amount of IO memory. So if this 31st bit set, we generated this VGA mem select, and we have here a register for our read data. So the write data we don't need to buffer because the write data is already coming from the Pico, from the RISC-V core. So we only need a buffer for the read data read back from the VGA core. So with this signal it's generated, and mind you, it took me 4 iterations to get this clean and this working. So with this signal it's generated, we pass here into our VGA core, we pass down here the select signal, VGA mem select. This ready is actually an output, you will see in a second. This ready signal is basically when our VGA core delivered data. Otherwise we pass down here directly this IO mem write and address and write data, and the read data, it's also an output which you don't see here instantly, but this is an output for our connecting this here to our VGA mem read data. To actually use this data, I extended this on positive clock here because we had here our IO mem, IO GPIO LED data here. So basically because we need to assign this IO mem ready and read data are the signals going to the Pico sock, and to keep this here the most simple and readable, I just reuse the same signals here, basically making those IO mem lines this IO bus lines for the icebreaker extension here. So if this is not the GPIO stuff here, then it could be, so if it's then our VGA memory select signal, our wire generated above there, then transfer this data from the VGA mem ready and read data here, each clock the data we get from the VGA core. In the VGA core this looks like this. So this is our module, new. Previously it was freestanding, now we have the signals, so input select and output ready, the inputs for the write data address and the output for the read data. And here is then at the end we have on always positive edge clock, if not reset, and if select. This is our select signal we get decoded. The beauty is that our VGA core doesn't need to know on which address it is. The decoding and the address assignment is done in the icebreaker top module, and basically we don't care as long as we are selected. This is for us. So this could be flexible and changed for whatever other use. Then address for a test. I right now wired up a couple of addresses. So these are the address lines from the CPU. And right now I decode here a handful of addresses. Not sure if this is the most. This is already right now using quite some handful of logic elements. However, later we need to have way more anyway, so not yet sure how we will do it. But basically I decided this is a flexibility hardware design. You can, just like in software, you decide what kind of structure layout is just for a test. Later, of course, we want to read and write the whole frame buffer, but just for a test, I decided here address 0 is the hardware cursor that you already see here. Actually, if I would tune this in, so we have this hardware cursor from the previous videos, and now we finally want to move this also. So address decode 0 is the cursor X address, and we also, for simplicity, we also only use whole 32-bit words, because why not? We have half the address space anyway, so whatever. On address 4 we use cursor Y, and because this is only 16 bits, we expand this here to with 16 zeros hardwired to form the whole 32-bit address. So address decode 4 is cursor Y, address decode 8 also for the test I wired up here the cursor palette, so we have the foreground and background color. Previously, as you see, white and black, but now we want to change them. And for read and write, you see here this is 16 bits. I also implemented writing, so if the write byte here of the 32-bit word, if the first bit here is set, then transfer the lower 8, and if the second bit is also set, so this could be unaligned and byte addressed, the same here. And because the palette is 24-bit colors, 8-bit RGB, we have here, oh wait a second, is this actually a typo? Only here always live on YouTube. And then depending on, is it even? Yeah, I think this should be, alright, right, stream byte, this should be 4, yeah, these are 4 bits, so yeah, typo here live on YouTube. So the 8 bits transferred here, so this supports read and write decode just for this for testing. For the frame buffer it is more complicated because in the meantime I learned this dual port memory is not really dual port, and there are some constraints, especially with Yosef synthesis, so making this read and write work for the frame buffer is another day of development and research, so that is coming up next. But for the test I wanted to test this integration and show you how this is done in principle to implement here some system memory mapped I/O bus here in Verilog. So this is synthesized and running here right now, programmed already. Let's see, do we have comments in the audience? Some questions in the audience. Just a quick thing, reduce the amount of logic somewhat. When allowing the CPU to read back from the registers, it may be better to use a separate combinatorial max assignment. So you have to say always block another case which assigns the various registers to, okay. I will take a look into this. Welcome everyone, Electron, Ash and Christian and everyone. Amazing stuff that so many people tune in. So to show you this, I also, so this is implemented, of course nothing happens except, well, when it synthesizes. If this is invalid, then we get an error, but nothing really fun happens. So for some fun to happen, we also need to change some software, and we have here this firmware, and I implemented here some cursors. So now we are mixing Verilog with real firmware software written in C, and here you see the difference. That here we have our VGA memory mapped I/O at just what I said, the first bit set 80 something, 80 million or so, whatever, how you even, anyway, 800, many zeros, hex. This is similar to our programming on the S3 Verge and Voodoo and SJ Octane and PS3 and so on, just that now we have also implemented the hardware ourselves, and you see the concepts are similar. And so for this, by the way, I declared this better volatile meaning the compiler should not optimize it away and always read and write it from memory and not cache it and discard it and stuff. So I implemented here, this is some small prompt on the serial line that we can screen attach here, Pico RISCV, and I extended this here right now for testing with C for moving the hardware cursor and just for quick testing. And the code looks like this. You see in this case statement of serial data received and sent, we have here lower and capital case C. Cursor. In the meantime, so if it is lowercase, then increment by 4 the cursor address, and if it is uppercase, then subtract 4. Printing here, then yes, this firmware environment super rudimentary. So we don't have like pretty printf something, so this is a little bit, I just reused what was already existing there. So we have just print a string, just print a decimal. So for testing, we read this memory mapped I/O register that we just implemented here in Verilog. So this is 8 and many zeros, like 7 zeros hex. Here's the address. for the cursor, X, Y, and the palette. And so we read this back and print it out, and then we assign this VGI MMIO. If you are wondering why is this 0 and 1 and not 0 and 3, this is because I declared this as uint32 already, 32-bit words at a time. And yeah, so then we have a cursor variable. We increment this here and assign it, move X and Y direction just the same. And just for the, because to be fancy and test it fully, I wanted to randomize the palette. Initially, of course, just for testing, I implemented X and Y cursor. Of course, this wasn't working. It took me quite an hour to get this to work. And by the way, even my initial attempts even stalled the CPU. A fun fact, if you do not implement this correctly and you do not generate, for example, here this ready, this IO, MMIO ready bit, then you stall your CPU, and because you never have data ready, you completely cease execution of any further instruction, just in case you were wondering. Happened to me. But yeah, to randomize this, we read here the read cycle count from the RISC-V. Let me just, yeah, this is barely on the screen. So this is some random, like sort of pseudo random number, incremented here the CPU frequency clock. So we assign the foreground and background color to the cycles just for the test. And to show you how this looks, so we have this running here, this virtual USB UART. And let's zoom this here. You see the cursor there. Right now this is a power on default address for the hardware cursor. And as soon as we now type here, is it even somewhat, let me just, what kind of other scenes, oh wait a second, this is all wrong. Maybe like that or so. Also it's not the most readable, but whatever. So when I enter here C, then you see the cursor disappeared. That is because our signal is still a little bit off by something. But you see the cursor appearing there because we started at 0, 0. Another day I still need to analyze what is wrong with our video signal. Again, this is a video signal from Mika Elizabeth Scott and from Scamline YouTube channel there. I'm not really sure, maybe this is simply overscan or some other, I don't know, some strange stuff is going on. But anyway, we have here now the cursor that I should probably also focus. And each time I press C here, we move another 4 pixels over there and randomly change the foreground and background color. Amazing feat here. All the achievements unlocked, probably actually not the most visible. There's even no my cursor. No, even I don't see it anymore because, nah. There it is. Probably because of the fancy colors. You can also zoom in there for. Anyway, yeah, so this, as I said, this signal is still a little bit pixels off by 1. This is a blocking versus non-blocking Verilog statements that we learned the other day. But you see moving by 4 pixels, and yeah, the colors probably also still, yes, we can also move in this other direction. The colors still a little bit off by 1 pixel there or something, just with blocking versus non-blocking. But first I wanted to learn here more with the Pico integration, RISC-V, and also there you see how all the firmware, the software and hardware design fits together, how it is on the software side, what we usually do here with the low-level vintage stuff, Verge, Voodoo, ATI, NVIDIA, SGI, PS3 and stuff, how the software writes executed cycle by cycle on the RISC-V CPU here, right on the system bus, on the memory with all the instructions and architecture, some load and store instructions as seen yesterday in the just-in-time code generation, writing this here to the hardware getting these signals here on the system bus, either good old-fashioned either PCI, PCIe, just everything more faster, fancy, and so on, or in this system on chip. This is most likely if you buy a cheap RISC-V from eBay or Alibaba. I wouldn't be surprised if many of those 10 buck RISC-V implementations, most of them might actually use here this open source Pico RISCV. I would not be surprised if they do. And as you see, quite some achievement here. I have to admit, all of this is actually, also by the way, maybe I wasn't the most focused, maybe. I have to admit it was more work getting into or getting back into Verilog. Also at university I never used it that much, just a little bit, as much as you need to use it as a software guy, but certainly a very nice learning experience, and I hope you learned a lot and inspire you to do stuff, tinker, create, program, software and hardware. So yeah, this code, this video core, Electron Ash writes hardware cursor. Yeah, hardware cursor we've implemented some weeks ago, just like previously it was static, we couldn't move it. Now we can move it in software like you would do with a mouse here, of this fancy stuff. And also, yeah, palette. So we have 16 colors, text mode. Theoretically we could scroll it, we have 120, so this is 80 by 30 text mode theoretically, and just that for simplicity, it is right now 128 characters, so theoretically we could probably maybe even scroll it, or a graphic mode previously implemented here. The biggest thing is now to yeah, Electron Ash writes IS-40 has 128K bytes of on-chip SRAM. Yes, however, the 128K on-chip SRAM we use for the system memory. This is basically the RAM, the memory for the RISC-V CPU. What I'm using, it also has some 70 or so K byte dual port block memory, and I'm using some 48K or something, or some a little bit more. So the really tricky part is now, because due to the design constraints, the hardware limitation, it's apparently, I learned, not a true, the 70K byte additional, or whatever, was it even 70, whatever. Whatever K-bit that was this dual port, it's not, I learned from the experts, not true dual port. True dual port meaning some read write and read port or something. So apparently it's like not true, but only a read and a write port. And apparently, I'm not sure whether due to hardware or Yosis design constraints and limitations, apparently the experts told me it needs to be clocked. So the two ports, read and write, what do we need this for? We need this for we stream from, what do I even show here? We stream from the memory from one port. Ports meaning we need to access the memory from best case from two sides, meaning from one port we stream here the data to the HDMI transmitter, and from the other side, from the other port, we would still need to access the data for read and write from our software to actually read and write data, like generate fancy game graphics. So being this not being a true dual port, and due to clocking constraints, so Yoast is not sure if it's a hardware limitation, but at least the experts told me, who reverse engineered all this fancy stuff, at least right now in Yoast you need to have this in one clock domain. That makes it really tricky, because this means, so most likely I need to rewrite here all the code to have a, most likely I will write a memory module, like because right now the frame buffer looks like this, VRAM, and so right now I just say I want 16 bits of VRAM, some 8K text attribute and text and attribute, and I'm most likely to interface with this VRAM from the system bus here, because if I do this right now, Yoast tries to synthesize it, so it would be as simple as accessing it here, like transferring the data to the address read here from the write data, for example. However, if we write it something like this sort, just a proof of concept, you get the idea somewhere here in some case, this results, so this synthesizes really long, like for minutes, and then we have like some, we do not have enough logic elements. So what happens is, like, Yoast generates some super complicated code to clock and buffer these signals, and we need some thousands or 10,000s of logic elements. Also, what happens due to that, actually IOSys is not using the dual port block memory anymore, but is using regular flip-flops, regular logic elements for this implementation. So due to this, we will most likely create a dedicated dual port memory model to have this more under our control, and then interfacing this will be a little bit tricky. So this also means most likely that we will have to delay this, so to implement Verilog logic to only access the data in the VRAM from the Pico RISCV SOC in non-active frame buffer scan-out areas. So that means that our scan-out or video signal certainly needs to have priority, and we can only read and write here from the system bus when our video signal is in a blanking period there. But this is certainly work for a whole day or afternoon or something of that sort. In any case, I hope you learned something, and that is the update and to-do list. And then certainly we also need to do all the off pixel, all the details of one pixel off by one. You see we have here some repetition of not yet correctly blocking versus non-blocking statements. Let's see more questions in the audience. Welcome Danny, Andreen and everyone. So yeah, that is the update. And again, it was much more work than I expected. I expected this to go a little bit more smooth, but yes, quite some learning experience. But certainly I made all beginner mistakes for you to not make them and learn something. And now we have, with all the experience gained, a lot of work left to make this even nicer. Maybe just for the fun of it, because the issue is, to show you something, you see it's not worth for me to fix this off by one, because I can read this, you know, it's hello world FPGA, so yeah, whatever, I can read this, that's good enough. Or it's a little bit off, but yeah, whatever. Probably most people here, leave me in the comments below, probably many of you agree that it's more fun to do new features before fixing the bugs. You should probably not do this in commercial projects, but for this YouTube entertainment, it's probably more interesting to implement features and show you how to do it. This also means that most likely maybe next I will interface some sound beeping logic just for the heck of it before going through all the dual port memory and off by one fixing issues. If you have any comments and tips and tricks or want to work on this, leave me in the comments below. Help certainly highly appreciated. This also means, by the way, that due to this, we can already start to, the more we get this to work, we can write homebrew software, games and fun stuff here on this nice RISC-V thing. Let's see, what do we have in the comments? Could probably just clock the block RAM twice as fast, and then yeah, this also some expert on the Discord of Icebreaker said to clock the BRAM twice as fast if I have the frequency, yeah, like double data rate, something of that sort. Yeah, but maybe it's the recommendation I got is implement the memory as a module. That means we will have here some encapsulated module here for module dual port RAM or something, just to make our life easier and to not allow IOSys to do random stuff, because the issue is it's hard to work if you type something and IOSys, you synthesize it and IOSys synthesizes 10 minutes and then you see 100,000 logic elements used. I think the benefit of having a module for this is also to have faster design times and less error-prone design, edit and compile or edit and synthesize rounds. But yeah, we can certainly try this. Thanks for this tip and the reminder. But yeah, these are all the details we need to work on. Electron asks, how is each bit of the 16 word in the character buffer used? Enable, yeah, so this is entirely VGA or CGA, EGA, MDA text mode compatible. So as you can see here, do I show this? Yeah, I show this. So this is entirely VGA compatible text mode, like each BIOS is booting. I also made a dedicated video. Initially I had here 8 bits, but I realized 8 bits is not as good, because we need anyway for each character displayed, we need both 8 bits, the 8 bits for the character here, age for example, and the attribute. And again, this is entirely VGA or CGA, EGA, whatever, Hercules or whatever that was compatible in terms of foreground and background color. So it's a 4-bit foreground color, 3-bit background color, and 1 blink attribute. As you can see, blinking is already implemented, and entirely for the convenience compatible, PC compatible. And later I found out 16-bit is more convenient to have one address cycle addressing the text, character, position, and the attributes in one cycle. It's an VRAM here in the pixel clock. Here on data data not enable or X. So I preload this, but I need to totally rewrite this for complete correct use of blocking versus non-blocking. And you see here we read the next character and next attribute here from the dedicated 8 bits of the upper and lower half of this memory. Electron Ash writes, blocking versus non-blocking is very confusing. He still has trouble with this. Yeah, even in the previous video, even this paper of Verilog experts called out there that even many Verilog experts have even sometimes may not fully understand it. So that is why I made a dedicated video of that coding style that kills. Also with thinking about exactly when timing update and clock edge versus... So basically the blocking versus non-blocking is the non-blocking updates immediately, and the blocking, let's maybe double check this, but the issue is also, so basically the non-blocking updates at the end of the clock cycle. It sounds simple. The issue is that if I remove some of those, so with just equal is blocking assignment, and what we are using, so we are using here mostly non-blocking assignments, meaning that this updates, this is buffered, and this updates here, this propagates and updates at the end of the timing interval. The issue with this is that I said in the previous video, this code here is invalid and not working how I thought, because as this is non-blocking, this address is only updating at the end of the clock cycle, meaning we are using here the wrong. So when I wrote this, I wasn't really aware of this. And the problem is if I update this to a blocking assignment, meaning that this is assigned immediately, then our design is blowing up again and we use some 1000 more logic elements and whatever. So I will most likely start from scratch and with signal generation. And because the problem is with a more complex design like this, if you start making changes, especially with this blocking versus non-blocking, you better design this correct from scratch, otherwise you get all kinds of strange interaction if you tinker now with this design that is not really correctly designed. Humans usually aren't so good at this off by one things. Actually it's the other way around. Humans are very good at doing off by one things. Like humans are very good to do things off by one actually. But yeah. Electron Ash writes, would we need to have some basic polygon rasterizer working on the icebreaker, but it would need to use 4-bit color or something to have this 32 by, what you saying, polygon, what do you mean with polygon rasterizer exactly? It's often a good idea to put larger memories in a module anyway, so software will often try to access random parts of memory and not interfere in a linear memory block. I need to higher half for the recommended to use all non-blocking statements for clock always. It's recommended to use all non-blocking assignment for clocked always blocks. Apparently he usually just does it and have some other combinatorial logic in an always or always FF block. Yeah, the issue is, I mostly wrote this here for readability. We wouldn't have this issue if we compute this address and directly use it in this VRAM. But this is just the habit of keeping it readable. Sometimes is a coding style that kills, according to this previous video. So keeping stuff readable and assigning this is exactly what you don't want to do, wasting cycles and stuff and so on. So yeah. Polygon rasterizer, like older video where was attempting to implement RDP part of Nintendo. Okay, cool stuff, need to check. You probably mean like sprites, or do you mean like sprite control stuff? Anyway, certainly a super nice learning experience, and maybe something that more software developers should do to better understand how hardware works. Certainly always if you do new stuff, especially if you don't need it at your daily job, but just to learn more and understand things more. In my opinion, something that many people nowadays do not do enough. Many people, when a decade ago it was Java, everyone at university only learning Java, not understanding machine level logic signals anymore. And nowadays it's of course a JavaScript, just trial and error, randomly changing HTML and JavaScript until it does something in some browser without even understanding not only operating systems or machine or, God forbid, hardware logic elements. In any case, let's see, I hope this is to keep these videos short and motivate people to watch them. It's probably best to end this now and continue another day. And you should be able to use T80s in this clocked Zen. What are you saying? What it's recommended. So what Electron Ash might do is for the assignment of to T address, there is to declare T address as a wire, then do a direct assignment outside of this always block. Should be able to use this T address in that clock block. Do I type quite a lot? I can never tell. What do I type quite a lot? I can never tell. Couldn't agree more about this low-level programming thing. Know more people about hardware level. Definitely helps when coding higher level languages. Yeah, also, this is also my opinion why many people don't even understand lower level parts. They just reduce modules. This is also most likely one, not the only, but certainly one reason why we get increasingly a software stack that more often than not doesn't really work anymore. Everything just put on top of modules, layers on layers, and nothing really works 100% correct in corner cases and off by one scenarios anymore. And many people don't even know how to do low level stuff anymore and just are helpless and can't even help themselves if it's not some module, some JavaScript framework, something, then yeah, YOLO. Anyway, that's it for today. Maybe leave me in the comments below what you would like to see with this most. Sound next, or fixing this video signal off by one stuff next, and similar stuff. If you want to contribute, this is already on GitHub. So GitHub, I have some Pico fork with this code inside, so that would be repositories Pico RISCV, and here you see commits and most of the stuff like firmware test VGA palette, for example, I committed already on the 2nd. You see here just what I showed you. Do I even show the right, hopefully seen here. And wire up, for example, here wire up VGA access here you see exactly this commit. Previously I tested around, it didn't really work, so this is exactly this commit that wired up here this system bus integration. And if you want to implement stuff, then be my guest and send some pull requests and patches to fix some off by ones or implement some more features. I hope you enjoyed this and learned something, and as always, interesting to hear from you, especially patches and comments and tips and tricks. And I hope to see you soon for all the next videos and live streams to come.